Good afternoon. We will see thermodynamics in this class. We are going to see zeroth law of thermodynamics, internal energy, first law of thermodynamics, thermodynamic processes. Zeroth law of thermodynamics. If two systems A and B are separately in thermal equilibrium with a third system C, then the systems A and B are in thermal equilibrium with each other. This is called zeroth law of thermodynamics. Suppose the temperature of system A is TA and temperature of system B is TB. Temperature of system C is TC. If A and C are in thermal equilibrium with each other, then TA is equal to TC. In B and C, if B and C are in thermal equilibrium with each other, then TB equal to TC. So in this case, TA is equal to TB. Every system, solid, liquid and gas, possess certain amount of energy called internal energy. Internal energy is the energy of the system itself. So kinetic energy and potential energy forms internal energy. Every system possesses a certain amount of energy. This is called internal energy. This internal energy is denoted by U. Internal energy of a solid, liquid, gas consists of kinetic energy and potential energy. Internal energy of a solid, gas and liquid consists of two parts. One is the kinetic energy, next one is potential energy. Kinetic energy is due to the motion, translational motion, vibrational motion of the molecules. Kinetic energy, potential energy is due to the configuration of the molecules. Internal energy is denoted by U. Change in internal energy of a substance is denoted by del U, delta U. Delta U is equal to NCV del T, where N is equal to small m by m. Small m is the mass of the substance and the capital M is the molecular mass. CV is the specific heat capacity of the substance at constant volume. Let us consider an example of water in a beaker. Beaker contains water. The water consists of water molecules, right? So here the molecules move each other. Therefore, internal energy IE is equal to kinetic energy of molecules plus potential energy of molecules. Potential energy is due to its position, due to its configuration. Kinetic energy is the moment of molecules. Therefore, the moment, rotational, translational moment of molecules. Therefore, internal energy is the sum of kinetic energy and potential energy. Here, intermolecular force of attraction is not considered. So here without considering the intermolecular force of attraction, we find the internal energy is kinetic energy and potential energy. When the temperature of water increases, say from 20 degrees centigrade to 30 degree centigrade, then change in internal energy is equal to M CV del T, where CV is the specific heat capacity of water at constant volume, M is the mass of water, and delta T is the rise in temperature. Therefore, when the water is heated, for example, if the water is heated, the increase in internal energy can be given by the formula mCV dt, where m is the mass of water and Cv is the specific heat capacity of water at constant volume, and delta T is the rise in temperature, which is 30 minus 20, 10 degrees centigrade. So this is the increase in internal energy if the water is heated. When heat is supplied to a gas, consider a beaker containing a gas, right? So here this is consider a piston cylinder arrangement. The cylinder contains a gas. Let the gas be heated by a source of heat. The gas, let the walls of the cylinder be accurate conductors of heat. So what happens when you heat the gas expands. It absorbs the heat and it expands. Therefore, the heat absorbed by the gas is utilized in increasing the temperature of the gas and as well as in doing the work by the gas. Therefore, the work is done on the gas. The work is done by the gas. Because of the work done by the gas, the gas expands and it pushes the piston up. Therefore, what happens is, according to the law of conservation of energy, the internal energy, increase in internal energy of the gas heat is absorbed by the gas, and because of the heat, internal energy increases and work is done by the gas. Therefore, increase in internal energy del U is equal to delta U is equal to delta Q minus delta W, where delta W is the work done by the gas and delta U is the increase in internal energy of the gas. So here, if we write this equation, delta Q is equal to delta U plus delta W, where delta W is the work done by the gas and delta U is the increase in internal energy of the gas. Therefore, heat supplied to the gas is absorbed in increasing the internal energy and as well as work done by the gas. This is the first law of thermodynamics. Therefore, according to the first law of thermodynamics, heat supplied to the gas is equal to increase in internal energy of the gas and work done by the gas. When heat is supplied to the gas expands. When the gas expands, it does work against the piston. So the work done is positive work done. Therefore, when heat is supplied, it is delta Q is positive, delta W is positive, and internal energy of the gas will increase because of the heat supply, the temperature of the gas increases. Hence, the internal energy of the gas will increase. Therefore, delta U is positive. When heat is rejected by the gas, then it is negative heat. It is negative. When the work is done on the gas, when the piston is pushed down, work is done on the gas, then this work is a negative work. The internal energy of the gas, in this case, right, it may decrease. Sorry. If heat is rejected by the gas, then it is a negative heat. If work is done on the gas, it is negative work. If the internal energy of the gas decreases because of the decrease in temperature, then it is a decrease in internal energy. It's a negative. Thermodynamic processes. First one is isothermal process or constant temperature process. In isothermal process, the temperature remains constant. The system moves from state 1 to state 2. Let V1 is the pressure at state 1 and V1 is the volume of the gas at state 1, and P2 is the pressure of the gas at state 2 and V2 is the volume of the gas at state 2. It's an isothermal process, therefore temperature remains constant. Therefore, this is governed by the equation PV equal to constant, where P is the pressure, V is the volume, C is equal to constant. Therefore, in isothermal process, P1 V1 equal to P2 V2. This is the governing equation for isothermal process. In isothermal process, because the temperature remains constant, the internal energy remains constant. There is no change in internal energy. Therefore, del U is equal to 0 in isothermal process. We know that delta Q is equal to delta U plus delta W. Therefore, heat supplied here in this equation, delta U becomes 0. When delta U becomes 0, delta Q is equal to delta W. Therefore, heat supplied is equal to work done by the gas. Therefore, here the gas expands from state 1 to state 2. When it expands from state 1 to state 2, the pressure becomes from P1 to P2, volume becomes from V1 to V2. Volume increases, pressure decreases because it is the expansion. This is governed by the equation PV is equal to constant, where here temperature remains constant, therefore PV is equal to constant. This is the governing equation for isothermal process. So here temperature remains constant, therefore heat supplied to the gas is equal to work done by the gas. Heat supplied to the gas is equal to work done by the gas. Change in internal energy of the gas is 0 here because there is no change in temperature. it is isothermal process or constant temperature process, hence there is no change in temperature, hence the internal energy remains constant. Therefore delta work done during isothermal process is given by W is equal to integral V1 to V2 P dV. So here the system, the gas expands from state 1 to state 2, pressure decreases, volume increases. Therefore the volume changes from initial volume V1 to final volume V2, where this is the work done, area under the curve. This area under the curve is the work done by the gas. So here increase heat supply to the gas is equal to work done by the gas, because the temperature remains constant, hence there is no change in internal energy. Let us derive the work done by the gas. Let us derive the work done during isothermal process, work done by the gas during isothermal process. The gas goes from state 1 to state 2. So here let us consider a small rectangle, right? The breadth of the rectangle is dV and height of the rectangle can be called as P. Almost it's very small change. Let us consider this as a rectangle, equivalent to a rectangle. This to find out the entire work done, we have to integrate this rectangle from state 1 to state 2. That is the work done, that is the area under the curve, this curve. So this is the work done by the gas during its expansion. Therefore, work done W is equal to integral P dV. Integral P dV. So here P can be got from the equation PV equal to constant. Therefore, P equal to C by V. Therefore, C by V into dV. So it becomes C into integral dV by V. So C into natural logarithm of V2 by V1. By integrating it, we get V2 by V1. So work done is equal to C into natural logarithm of V2 by V1. P1 V1 equal to P2 V2 equal to constant. This is the equation we know. So work done is equal to P1 V1 natural logarithm of V2 by V1. Converting that into common logarithm, the work done equal to 2.3 into P1 V1 log V2 by V1 base 10. This is the work done by the gas during its expansion. So work done by the gas is equal to 2.3 P1 V1 log V2 by V1 base 10. We know that P1 V1 equal to P2 V2. So from that V2 by V1 equal to P1 by P2. Substituting that, you get W is equal to work done by the gas. W is equal to 2.3 log P1 by P2 base 10. This is the work done by the gas. W is equal to 2.3 log P1 by P2 base 10. A process in which no heat enters the system or no heat leaves the system is called the adiabatic process. So here there is no change in heat supply, therefore del Q is equal to 0. No heat enters, the del Q, change in heat is 0. This is called adiabatic process. Here consider a gas inside the cylinder, and inside the cylinder it is constrained by a piston. So here assume that the cylinder is completely insulated. Therefore, no heat can enter enter the gas through the cylinder, and no heat can come out from the gas through the cylinder. It is completely insulated, right? So in this case, delta Q is equal to 0. Delta Q, we know that according to first law of thermodynamics, delta Q is equal to delta U plus delta W. Delta Q is 0, therefore 0 is equal to delta U plus delta W. Therefore delta W is equal to minus delta U. Therefore work done by the gas is equal to decrease in internal energy. Right? When the gas expands, work is done by the gas. When the work is done by the gas, the internal energy of the gas decreases. When the internal energy decreases, this internal energy decreases because the temperature decreases. When the work is done by the gas at the expense of its internal energy, the temperature of the gas decreases, internal energy decreases. So adiabatic process is governed by the equation V power gamma equal to constant. Here let us draw a graph here, pressure on the x-axis, y-axis and volume on the x-axis. The gas goes from state 1 to state 2. Volume increases, pressure decreases. This is governed by the equation P V power gamma equal to constant, where gamma equal to the ratio of specific heat capacities of the gas. Cp is the specific heat capacity of the gas at constant pressure. Cv is the specific heat capacity of the gas at constant volume. So gamma is equal to Cp divided by Cv. So the equation is P V power gamma equal to constant, P1 V1 power gamma equal to P2 V2 power gamma. Work done during adiabatic process. So here this is the pressure volume diagram or PV diagram. The gas expands from state 1 to state 2. Pressure becomes P1 to P2, volume becomes V1 to V2. Consider a small infinitesimal volume. Consider this as a triangle because it takes almost at constant pressure. It expands at constant. Let us derive the work done during adiabatic process. Consider the PV diagram, pressure volume diagram. The gas goes from state 1 to state 2. Pressure decreases from P1 to P2, volume increases from V1 to V2. Consider a rectangle, a small, this is dV and this is P. Therefore, we have to integrate the area of the rectangle between V1 to V2. Therefore, work done is equal to the integral V1 to V2 P dV. P is equal to C by V power gamma. Gamma is the ratio of specific heat capacities of the gas. Gamma equal to Cp divided by Cv. So P is equal to C by V power gamma. During adiabatic process, W is equal to integral V1 to V2 C divided by V power gamma dV. C constant. So C into integral V1 to V2 dV divided by V power gamma. Then is equal to C into V1 to V2 integral V1 to V2 V power minus gamma dV. C into V power minus gamma plus 1 divided by minus gamma plus 1. Right? From V1 to V2. So W equal to C divided by minus gamma plus 1 into V power minus gamma plus 1 V1 to V2. Work done is equal to C divided by minus gamma plus 1 into V2 power minus gamma plus 1 minus V1 power minus gamma plus 1. So here you multiply this C inside. So it becomes 1 by minus gamma plus 1 into C into V2 power minus gamma plus 1. Again C into V1 minus V1 power minus gamma plus 1. So here you substitute here next step. Substitute P2 V2 power gamma here. For here we have V2, therefore P2 V2 power gamma. Again here P1 V1 power gamma. Work done by the gas is equal to 1 by minus gamma plus 1 into P2 V2 minus P1 V1. Simplifying the equation, we get this. We get this equation. So work done is equal to 1 by gamma minus 1 into P1 V1 minus P2 V2. PV equal to nRT, P1 V1 equal to nRT1, P2 V2 equal to nRT2. Therefore, work done by the gas is equal to nR divided by gamma minus 1 into T1 minus T2, where n is the number of moles and R is the gas constant. Isobaric process or constant